You know, this week in Cincinnati, we had an opportunity to spend some time in the facility that is beginning to make Karno, the technology from Hyliion Holdings, a reality. Now, Karno, which really comes from an engineering term, is a generator that can operate on multiple fuels, but it's not an internal combustion engine. It's the opposite. We're going to hear about all of that today from Josh Mook, who's the Chief Technology Officer, as well as a conversation with Thomas Healy, the CEO of Hyliion, who had to kind of push pause on the original plan for the business, which was going to be Class 8 trucks. Now it's all about the Karno. Hope you enjoy it. I'm with Josh Mook, who is the Chief Technology Officer for Hyliion, and the whole idea of the Karno generator, which is sort of the second life for Hyliion, really rests with Josh. Josh, you've been with this for how many years?
I've been working on this technology for 6 years.
6 years. And that started at General Electric, where you came
Correct.
from. And
Yep.
you spent, 2 decades?
I was 20 years at General Electric doing engine design for all kinds of aerospace applications.
All right. Now, we're not doing aerospace now, but we may as well be, because this is pretty complicated stuff. I need you to help the audience kind of get through it. So this is obviously the Karno behind us, or next to us here. And maybe you can kind of give us a quick overview.
Yeah, absolutely. So the first thing to think about in the Karno power system is it's a linear heat engine. And I want to put the emphasis on heat engine. So it runs fully off of heat inside of the system and not off of a rapid chemical reaction like you think about in like an internal combustion system. So very, very, very different. And so what you're seeing here is each one of these shafts, you can see 4 of them located here next to me, is about 50 kilowatts of total output for a total package of 200 kilowatts, which we have here. And what's really, really interesting about this heat engine technology is that we can take almost any fuel or any heat for that matter, and bring that into the sealed system, which happens at this interface where my hand is located, and use that to create a clean electricity out of it.
Now, there's no oil, there's nothing, no bearings. Well, there are bearings, but they run on air, is that right? You've got helium inside?
Yeah, so the entire system, and if we kind of walk around here, from this location to this location, is fully hermetically sealed, right? So we seal it at the factory, we fill it with an inert gas, in this case, helium, and then it stays sealed like that for its entire life. All we're doing is heating and cooling that inert gas over and over. The bearing system, as you mentioned, or how we don't get any wear through the system, is that floats on a cushion of that helium that the system supplies.
Okay. And basically what's going on inside here, you've got heat and cooling sort of next to each other all through here. The business end is what? Is down here where you would put the gas?
Yeah, that's where the fuel goes in. The fuel goes in on the end. So I like to think about it as it's cold in the middle, it's hot on the ends, right? So we put the fuel in, we create the heat. You can see this engine's been through about a year's worth of testing to give you an idea. And you can see sort of the heat staining. That's very normal as that material sort of ages. And then you'll notice it transitions from, what was hot to what was cool here, right? So what we're doing is we're taking that heat in, expanding that gas, pulling that energy out of it, cooling it back down, compressing it, and then just repeating that cycle over and over again about 20 times per second.
Okay. And ultimately you're taking out what, about 50% electricity?
About 50% electricity of the total heat input, and then the remaining can be used for like hot water or building heating or other uses for that energy.
Okay, great. Josh, this is clearly where we're going to get something really hot. We're not going to see it right this second, but basically you're testing different fuels in here and that sort of thing.
Yeah, absolutely. So this entire lab space that we're in right now is where we do a lot of our development of the reaction process. So taking that fuel in, mixing it with air, reacting it to get the heat ultimately that we need, and doing so at a very low emissions output. It's really important for us to have extremely low emissions, especially for your regulatory emissions like NOx and CO. And so what we do in this entire lab is develop those fuel schedules, test different hardware, different concepts as we maybe continue to evolve these systems over time. And what's really neat about this particular setup is that it's a quartz. We've replaced some of the metal with quartz so you can actually see inside of it. And when you do that, it allows you to really see that it truly is a flameless process, right? There's no visibility to the flame. All you can see sometimes is sort of the metal getting hot.
This is important because when you talk about NOx, you talk about emissions, this is not internal combustion, it's this external combustion engine.
Yeah.
I'm not sure I fully understand that, but the idea being basically that your NOx would be lower because you're burning, but you're not really combusting.
Exactly, yeah. So there's no visible light in this process. We have very low what's called radical formation, which normally will lead to NOx and CO and other things. So the way to think about it in the easiest way is this is a very low temperature reaction process that is continuous. It's not starting and stopping. It's continuous and it's low temperature. When we do both of those things together, we can get all of these classified reactants like NOx and CO down to near zero levels, which is really, about as good as you can get. And that is enabled from the fact that the power system, right, the system where we're pulling the energy out, is completely and physically disconnected from the heat system. The only interface between those is a heat exchanger.
Okay. So when we talk about EGR, for example, exhaust gas recirculation, that's what's happening. It's a kind of an EGR system. Or?
So there is, we do recirculate exhaust gas inside the system, but it's very different than what you would see in like if you're used to like diesel exhaust gas recirculation, where you have a lot of soot and issues with like EGR clogging. That is not at all what we're doing. We're basically in the flame zone recirculating some of our combustion product. And as a result, we can continue to drive down those emissions, continue to drive down fuel usage.
Right. And you're not getting particulates, not getting
you don't get any soot, you don't get any particulate out of this. It's very clean through the whole process.
So Josh, here's the thing. I know just a little bit about additive manufacturing. This is a great example. Can you start here with the powder? You've got two powders.
Yep. So in additive manufacturing, right, what we're doing is we're essentially taking a geometry, breaking it up into individual layers, and then welding or melting those layers successively to build a full part. So all of our raw material is the same powder. What's really cool about additive is not only is all the raw material powder, but we recycle it through the process. So anything I don't use to make the part goes back into the front end and recycles. So it's a near zero waste process, number one. Then what I do is I start with, a blank canvas, so to speak, and I start building that part up layer by layer. And so this is a good example of what we call the reactor. The reactor is about halfway done in this case. And what's really neat is you can see some of the complexity that's inside that you could just not achieve any other way.
There's no way anybody can make this.
It's not possible, right? I mean, the amount of complexity and joining and welding and things would be nearly impossible to do. What's really the reason we do it is not because we like to make really hard things. It's because our whole system hinges on the ability to transfer heat from that fuel that we just reacted into the system and do it very efficiently. This kind of heat exchanger that you're seeing here can do that with capturing 90% or more of the heat, which is sort of unheard of from a classical engineering perspective. So as the part continues, it eventually finishes, and then, we take this part, we do a couple little touch-ups on it from a machining standpoint for connections and things, and then bolt it onto the engine. So the engine really consists of 4 major parts. You have the generator, the cold side, the hot side, and the reactor. Those last 3 parts are all additive. You just bolt them together, stack them up like a cake, and you're done.
Well, one of the questions, about additive, it's usually a prototype type of application, but there really is the opportunity, you think, to do at least low volume manufacturing. If you just get, as behind you, all those machines, you get enough machines, you can do this.
Yeah, I think the thing, the difficulty with additive traditionally has been engineers have taken components that are maybe suitable for casting or suitable for machining and tried to use additive to make them. That's not really a good fit. In those cases, they're going to cost more. You may get them faster, to your point, rapidly, but they may cost more. They wouldn't give you any inherent advantages. What we've done is we've completely rethought a system that can only work with this sort of level of complexity. And now, it's completely changes the game on how you want to produce those parts long term.
Sure. So Josh, the doors are closed, right? but this is really where the action is, isn't
That's
it?
right.
Go ahead, do the dramatic thing and open them up.
You bet. Let's open up the system here. So this is our full system. So what you're seeing is the engine that you saw in the other room, but now installed in its sort of final configuration and connected to our high voltage source here, which can allow us to power the building or really power anything that needs electricity. Fuel in, power out.
125 kilowatts, that's pretty beefy.
Yep.
But you're on your way to 200 kilowatts.
That's right. Yeah, so our alpha system, which is what you see here, is 125 kilowatt net output. On the beta system, which is what we're building, you saw us building on the additive machines, is the same physical size and shape. It really looks, from the casual observer, will look identical, but produces 200 kilowatts of continuous output.
So these then, of course, you're going to pretty it up before you give it to anybody.
Yeah, of course. A lot of instrumentation on here. What you're looking at right now is an engineering asset, right? So it's got about 200 or more pieces of instrumentation, temperatures, pressures, lots of data that allow us to correlate our models, verify that all our predictions are exactly what we anticipate them to be, so that we can deploy these in the field with high confidence.
Excellent. Josh, thank you so much. Awesome. Thomas Healy, here we are again. I mean, it's like, I love talking to you, and that's good because we do it an awful lot.
We do.
But either on the phone or here in person, you know, this is sort of son of ACT Expo last year. You took us through the Karno in where were we? In Anaheim, I guess.
Yeah.
And, you know, I think, you know, now you're actually in early test production. You've got a few customers lined up. You know, the most amazing thing to me as we talk about startup companies is this is your second chance. I mean, as sad as seeing the Hypertruck, you know, at least go on pause, if not go away altogether.
Sure.
You know, this is something that you seem to be throwing everything into now.
We are. So for anyone who's not completely familiar with the story, so we really had two businesses under one roof, right? We had the powertrain technology for Class 8 semis, and then we had this Karno technology, which we really saw as it was going to feed into the semi-truck. We always knew that there was a stationary power element of providing power to the grid with Karno, but the focus was trucking. As we saw, just the landscape of trucking change, the pullback in people's adoption rates of EV, the push out of mandates, we just saw that it wasn't a sustainable economical solution to stay in that space. You know, we were burning about $150 million a year of capital across the two businesses versus we were able to push pause, as we mentioned over here, and now we're on about a 40 to 50 million a year burn rate working on the Karno technology. But as you said, all the eggs are in this basket right now. This is the focus of the company.
Well, it's interesting because, you know, we talked with Josh Mook about the whole idea of additive manufacturing. You think of additive manufacturing and you usually think of prototyping. You're not thinking of production, but there really is. And apparently you're, you know, loading up down in Austin now with more you know, additive equipment to make these parts. The parts themselves are so complex, they really couldn't be made any other way. But is scaling realistic for this?
So it is. So additive has pros and cons, right? The pros are you can make parts that you could never even have imagined, or you could only have imagined, you could never have manufactured before. The cons are it's not as cheap as CNC machining or putting it on a lathe, but you couldn't make the parts we're making on those types of machines. So what we've designed with the Karno is we're taking additive, using it as an unlock to make something that couldn't have been made before. So that's where additive really works well. Now, the question is, you know, as you said, can you scale this? Can additive actually grow with you? So one of the nice things with additive is as we're going to scale production, you know, if we were a conventional engine maker, you'd be looking at probably what, a $500 million factory that you need to set up just to make engine number one coming out of the end of it, right? For us, we can buy a machine, millions of dollars, but you know, not a $500 million, but buy a machine and that can start producing Karnos. Then as we want to scale volume, then you buy more machines, then you just keep on stacking those together, and that's how you scale. So Is it as cheap as conventional manufacturing? No, at least not today. But is it economical to where we can provide a solution at a price point where it solves a real problem for the grid? It is.
Well, and I think we have to talk about the grid because, you've outlined 4 areas that you want to work in. Obviously, from a FreightWaves perspective, we look at, what are you going to do for infrastructure for electric vehicles? We've talked about that a little bit in the past. And it is one of your target areas. That is, adding, you say it could be primary power rather than secondary power, but,
Correct.
Either way, adding to, say, some of these infrastructure sites, they're coming up everywhere, and perhaps you could be part of that. Do you see that as a early target for you?
It is. So the 4 buckets we mentioned, we've got EV charging, right, which is the FreightWaves, the focus. We have using waste gas, so landfills, oil and gas sites. We have prime power for facilities, and then we have mobility, which, as we talked about today, one of the early applications we're going after is marine. Not yet into the on-road application, but we'd still have that on our roadmap for the future. It's just not going to be one of the early adopter focuses. But the EV charging side of things, I mean, as I'm sure you've heard just as many times as I have, fleets go to the utility, they ask, hey, can I get this power? Either the answer is 1 to 3 years, you can get an interconnect, or no, there's just not enough capacity at all to be able to provide the amount of chargers needed. And so that's where we're able to come in and give, the view is give more of an immediate deployable solution that can also grow with the fleet, right? We're fuel agnostic. So maybe the fuel today is natural gas, but maybe the fuel in however many years is going to be hydrogen. You can get one set of hardware today that can kind of bridge that journey with you.
Well, speaking of bridging journeys, I mean, you've come that way on hydrogen. I mean, I can remember days when you had not a lot of ease, but mostly because it wasn't ready, and it is still obviously an immature infrastructure for it. But the idea of burning hydrogen, and we have to mention, of course, that the Karno really doesn't create a lot of NOx, and because you're not an internal combustion engine, So let's get that out of the way first. But this idea that there is an opportunity for hydrogen and for a number of other fuels. How many fuels have you tested at this point? I know you had, a waste gas out in the Permian Basin.
Yeah. So I know natural gas is our primary tester, right? We've done propane, we've done hydrogen, we've done the Permian Basin gas. I think there are other ones as well, but what we're doing is we're using the same fuel injection technology that is used in many of GE's aerospace engines, as well as in their power plants as well. And they have certified or tested over 20 fuels that this type of fuel injection technology can be utilized with. So we haven't necessarily run all those fuels through the Karno, but we know that the technology does work for those fuels.
Sure. It's interesting, and as we tape this, it's the week when GE split into effectively 3 companies.
Yes.
This actually came well ahead of that. I think it was 2021 or 2022.
It was right after the divestiture was announced. Over a year ago.
And so you brought with you, and I didn't realize this, you brought with you at least a dozen of the GE people, including Josh Mook,
Correct.
Your CTO, who know this intimately and know this area intimately. What does that do for Hyliion in terms of not having to sort of invent it from scratch?
Yeah, so this technology, I mean, we've been involved in it for a couple years, but the reality is it was within GE for, I think we're in year 6 now of kind of when this was thought up. Now, before that, many of the team, like Josh and others that you met, were actually in the additive business within GE. And this kind of became a project with, half a decade ago where they made these additive machines. They were looking for a technology that could kind of go use additive at scale, right? The aerospace industry is already using additive, but there's only so many planes made every year, right? So that's where the team came up with this idea for the Karno technology, because they did see that there was going to be this shortage of supply of energy on the grid. And, GE also is in the energy business, right? So they know that there isn't as much adoption of new power plants right now. But there's a rising increase of demand on the grid.
Well, and here in Cincinnati or suburban Cincinnati, where we are, not too far away, they make jet engines. I mean, that's they
testing
here.
grounds are not far.
Yeah, and from here, I guess I'd leave you with this. Again, I picked up as you presented that this is something that you're all in on now. I mean, this is not, we're not,
Focus of
because
the
it'd be okay if you were maybe a little confidence bruised after having to pause the Hypertruck, but you don't seem that way. You seem like you've pivoted entirely into making this go.
Yeah, so the focus now is Karno. There's definitely an element of just make sure we're going about this as logical as possible, right? We reduced down the size of the team. We drastically reduced our burn rate from where we were and put ourselves in a position where we started the year with a little under 300 million of cash available to us. We want to be very smart and wise with that, but we also do want to go scale this, right? That's why we've recently mentioned, we're going to start setting up manufacturing in Austin. Now, as we go scale, we'll need to set up more and more printers, and that's probably not something we'll do on our balance sheet necessarily, but we'll look for either equipment financing, things like that, to go and really go scale this. But the focus for this year, as we shared today, is we got to get this out into customers' hands, right? And we have the customers lined up for later this year, many of which were actually here today, and so we'll get these units out there, and the goal is prove the performance metrics we've been talking about out of the Karno, prove that in customers' hands, because that's what the market's looking for.
Sure. Hey, I got to ask you this. Where did the name Karno come from?
Yeah, so it's a spin on the Karno cycle, but C-A-R-N-O-T, so an engineering term, the cycle of engines. So it's a spin-off of that, but with a K-A-R-N-O.
Okay, very good. Always good to see you.
Yeah,
I look forward to seeing you next time.
Appreciate it.
Thanks. Okay, there will be no quiz, but at least you understand more about the Karno technology now and how Hyliion Holdings plans to make it into scaled production. Yeah, there's a lot of additive manufacturing here, but they believe if you can just get more machines and do the things that these machines already do, there's a business here. We're going to find that out. Thanks for watching.